Hey guys, Mr. Gibson here. So this assignment is just like your other interactive notes and summary overviews where you have the Kami and you fill in the blanks using the information here. So very straightforward. And so this video again is just going to be me going over the summary overview, making sure that you have the right answers. So if you have not done that yet, I urge you to pause the video, go back and do that, and then watch this video again because I go pretty fast, because hopefully you are just checking your answers, not writing them down for the first time. Okay, so I'm going to give you 2 days to complete this once again because it is quite a bit of work. And so let's go ahead and open this up with Kami. Any day now. All right, looks like it's trying. All right, finally loaded. So hopefully, like I said, up to now you've filled in all these blanks. These questions here are again for you to use to study. So if you're not sure what to study, instead of just going back and reading word for word, you can go through and quiz yourself on these questions and the summary page. All right, so what we're going to do here is just go over this one summary overview page. Hopefully it will not take us too long since some of these are multiple choice. That's pretty straightforward. All right, so number one says briefly describe the following properties of light, and it wants you to define amplitude, wavelength, and frequency. So I've got a text box here. Having colors other than black is super helpful for me when I go through read, because I can tell what you've typed versus what I've typed. So amplitude, again, is the height of the wave from the 0 point, or where it's flat, to the crest. Okay? So if we were to look at a wave here, you can see amplitude is just the height from the 0 point. So think of it as like sea level up to the top, the highest point of a wave, which we call the crest. Okay? So there's amplitude. All right. Wavelength of a wave is the distance between two crests of a wave. Okay? So when you have two waves next to each other, you count the distance from the crest of one to the crest of another, or the peak or the top of one to the top of the other, and that is the length of the wave, or the wavelength. Okay? And finally, frequency is the number of cycles that pass per unit of time. Now let me put that into more general terms. Frequency is how often the wave crosses this midpoint, or how often there is a wave. So wavelength is how far the waves are apart. Think of the amplitude as how tall the wave is, and the frequency is how often the wave crosses the midpoint, or how often there is a wave. All right. Next question. How are frequency and wavelength related? They are inversely related, or indirectly related. And what that means is, as one goes up, the other one goes down. As wavelength gets higher, meaning the waves get further apart, then the frequency goes down. So as wavelength goes up, frequency goes down, which makes sense, right? If the waves are farther apart, then it's not crossing that midpoint as often. But if the wavelength is really short, meaning the waves are not very far apart, then you have that wave going over the midpoint really, really fast. And so frequency would go up. So as wavelength goes up, frequency goes down. As wavelength goes down, frequency goes up. Okay, so what equation do we use to describe this relationship? Well, you can put a couple of different things here. I believe what was in your notes was that wavelength times, frequency equals c, which is the speed of light. So frequency times wavelength equals speed. And in this case, we're talking about light. We're talking about the wavelength and frequencies of light. So the wavelength times the frequency will always equal the speed of light. The speed of light is constant in the universe, as far as we know. It's 3 times 10 to the 8th power meters per second. So very, very fast. All right, so there's our equation. Wavelength times frequency equals the speed of light. And that equation actually describes that they're inversely related. When you multiply them, they always have to equal the speed of light. So if you increase frequency, you have to decrease wavelength for that equation to work. Okay, so they're inversely or indirectly related. So atoms are in the blank state when electrons are in the lowest possible energy level. We call that the ground state. Think of that like the ground floor of a building. They're in the lowest state or the lowest energy level possible when they're at their lowest energy level. Atoms are in the blank state when electrons are in their highest levels. They're actually at their excited state. Those electrons are excited. They're full of energy. Just like when you're excited, you're full of energy, right? Electrons are the same way. So what happens to electrons when atoms absorb or gain energy? So what happens is, I like to refer to it as jumping. They jump to higher energy levels, okay? Which makes sense. If it's gaining or absorbing energy, it's going to go to a higher energy level because now it has more energy. Let's look at that on an atom. So you can tell this atom here that's going from energy level 1 all the way up to energy level 5, it's absorbing energy. It's gaining energy, meaning it's not at this lowest energy anymore. Now it has so much energy, it can hang out in energy level 5. So a lot more energy there. Now, what happens to electrons when atoms lose or emit energy? They fall back to the ground state. So they're losing energy. And I'm going to add a little bit to this. They give off light. So here's what's going on. If you were to heat up an atom or with heat or with electricity, some way you're adding energy to an atom. And so its electrons are getting excited. They're absorbing that energy and going, like we said up here, to higher energy levels. But here's the thing. Just like if you were to go drink like a Monster Energy or a 5-hour, you would get like a lot of energy, and then what would happen? You would crash, right? So electrons do that too, except it doesn't take them nearly as long as us to crash it. They crash almost instantly. So they absorb all that energy, go to a higher energy level, and then almost immediately fall back down to the ground state. Now, here's the thing. Energy can't be created or destroyed. So when they fall back down, they've got to get rid of that energy somehow. And the way they do it is they give off light energy. They give off energy in the form of light. And so what you see up here, this electron here was absorbing energy or gaining energy. And now this electron is losing it. It's falling all the way from energy level 6 back down to energy level 1. So it's giving off that extra energy in the form of light. And that's actually what makes every bit of light that is hitting your eyeball right now. The atoms in your computer screen while you're watching this video are doing this because electricity is being conducted through them. And so this is how we see all light, from stars, from light bulbs. This is what happens in the filaments of light bulbs. It's pretty interesting. Now, what's really interesting is every atom does this differently, meaning that every atom, when it gives off light, gives off a unique wavelength or frequency of light because they all have different numbers of electrons. So what are the discrete lines of light given off by an atom? We call that the atomic emission spectrum. Okay? So the atomic emission spectrum. So for example, this is the atomic emission spectrum of hydrogen. If you were to put hydrogen in a gas tube and conduct electricity through it, it would give off light. It actually looks kind of like a bluish, purpley, almost kind of like Mace Windu's lightsaber just a little bit from Star Wars. We're just with the naked eye, but if you were to pass that light through a prism and refract it, you would see this wavelength of light, this wavelength of light, this wavelength of light, and this wavelength of light. So these 4 colors are what the electrons of hydrogen give off. And you would not see that for any other atom. It's unique to hydrogen, okay? We call that hydrogen's atomic emission spectrum. It's like their signature. It's not, or their thumbprint. It's not like any other elements. Okay, so number 8, for which the following transitions predict if light is going to be emitted or absorbed? Well, here we have an electron moving from n equals 3, which is energy level 3, down to energy level 1. So it's losing energy. It's going from high energy level to low. If it's losing energy, it is emitting it. It is emitting light. Emitting is the same word as like losing or giving off. Okay. Here we have going from energy level 2 to energy level 4. Well, if it's going from a lower to a higher energy level, it's gaining energy. It's not giving it off because it's getting higher. So it's absorbing energy. Okay. And then over here, energy level 5 to energy level 4, again, it's losing, it's going down. The energy has to go somewhere, so it's being emitted because it's going from high to low. All right, number 9, for the following transitions, circle the one that would give off purple light. So that's a tricky one. How would you know if it's giving off purple light? So let's go up here. You see these numbers are increasing frequency and decreasing wavelength, meaning, and you can tell just by looking that the waves going from left to right are getting more energetic, okay? So meaning that these forms of light on the right side are higher energies than the ones on the left. And so violet is a much more energetic light than red. Red is a relatively low energy wavelength of light. And so here our question was, which one of these would give off purple light? So we're looking for which one is giving off the most energy. Okay, so here we have A, it's falling from energy level 6 to energy level 1. So that's falling 5 levels. That's a whole lot of energy. Let's see if there's any others that can compete with that. B, we're going from 2 to 4. That's not giving off energy at all. It wouldn't give off any light. It's absorbing energy because it's going from low to high. C, we're going from 2 down to 1. So we are giving off energy, but we're only falling 1 step. And D, we're going from 3 to 1. So again, we would be giving off light, giving off energy, but it's only falling 2 steps. Whereas A, it's falling 5 whole energy levels. It's giving off that much energy. So what we would want to do is let's circle A. Whoops, didn't mean to do that. Where's the undo? Let's highlight A because A is giving off the most energy. Oops, sorry, and I did it again. Wrong place. I want to answer number 9. And so that one is giving off purple light because it's giving off the most energy. Okay, like how energetic that light is over here. All right, now number 10, for the following transitions, circle the one that would give off red light. So here we have 6 to 1. Well, we know it's not that one because we just picked that one for 9. We said that was giving off purple. Remember, red is lower energy. It's farther to the left on your spectrum here. See how big and not energetic those waves are? So we don't want to pick the one that's giving off a lot of energy. That would be purple. B, going from 2 to 4. Again, that's going up 2 steps. That's absorbing energy. It's not giving off energy because it's getting higher. C, we have going from 2 to 1, so it's only falling 1 step, so that's not a lot of energy, but it is giving off some. Or D, from 3 to 1. Well, red is the lowest energy color of light that we can see, so I'm going to go with the option that's giving off the least amount of energy, so I'm going to go with C. Okay. Number 11, in an electric discharge tube, the emission spectrum for helium is an example of, it would be an emission spectrum. So it's actually none of the above, okay? And number 12, what would an atomic emission spectrum look like if the electron's energy levels in an atom were not quantized, meaning that you couldn't pick out exactly what colors were there and how many there were? So like on that hydrogen we looked at, you could clearly see red, light blue, blue, and purple. What if it was all kind of blended together? Which is what happens when you maybe look at a really bright light like the sun. And so in that case, it would be in a continuous spectrum. We could tell generally what colors were there, but not exactly the wavelengths and frequencies, okay? would just be kind of a blur. So it'd be a continuous line almost. All right, so there you have it. There are the answers to the summary page. If you guys need any more help on that, feel free to email me or call me.